And the main question was not all of the reactions, but this first one, third one, and the sixth one, trying to understand why, we get the particular products we do here. All right, so when dealing with the carboxylic acids, the first thing that you will remember that we talked about in this particular chapter is that carboxylic acids are first and foremost acids. Okay, so if you react them with a base, and there's a lot of different bases out there, so be it something like a hydroxide, an alkoxide, I think we've used sodium hydride, where hydride's the base, NH2 minus, or even amines, which are neutral. All of these act as pretty good bases. So in the presence of a carboxylic acid, all any of these will do is just a simple acid-base reaction. Okay, so in the case of sodium hydroxide, I know what you're thinking it might want to do is add to the carbonyl, because that's what we've been doing, for this whole chapter. All right, but that doesn't happen in the case of the carboxylic acids with these reagents, because first and foremost they're acids, so the acid-base reaction happens first. So what this does instead, it grabs that proton. And you get this carboxylate. If you want to pair that up with a sodium cation, you can do that. And water. And that's all that happens. Okay, in the case of using the amine, once again, that amine's base. Yeah, question?
Back to the first one.
Yeah.
What if that said NaOH and dilute high?
Okay, so in 2 steps, like 1 and 2. If that were the case, like the NaOH step would do this. And then if you added the dilute H+, that would just reprotonate the oxygen. So no net change. Any other questions on that first one? All right, so the second one, we have a different base, but it's the same exact thing. Okay, so you're using the nitrogen with its lone pair as the base. It will first just react with that proton. Giving you the carboxylate, and then you get an ammonium ion. So instead of NH2, it'll be NH3 plus. And you have your negative carboxylate, positive ammonium, so that's a stable salt. And that's all that happens there. Then the last one here is sodium hydroxide, but then we add something else. So step 1 is no different than what we saw in the first reaction. So you react and get the carboxylate. Okay, but that oxygen being negatively charged is nucleophilic. So if you put an electrophile in there, it can react with that. So now if I add this acid chloride, Okay, that acid chloride, it doesn't have the same problems as carboxylic acids having an acidic proton. So the only thing that happens to these is nucleophiles add to the carbonyl carbon. So that's what we're going to do here. We're going to use this oxygen as a nucleophile. Add that to the carbonyl carbon. We've done that many, many times. That gives us this tetrahedral intermediate. And then at that tetrahedral intermediate, these almost always collapse. And those electrons will come back down to give you the double bond O. And you'll lose the chlorine as the leaving group. So that one can be used to make the anhydride. Or we did the Williamson ether synthesis, so you could just add an organohalide to this and put, say, an ethyl group on that oxygen if you wanted. Okay, now, these reactions in the middle here, like acidic conditions aren't problems with carboxylic acids because you're just adding acid to an acid, which doesn't cause any issues. It's just when you have the base interacting with the carboxylic acid. Yeah.
For unsymmetrical anhydrides, we don't need to know how to name them, right?
No. Any other questions? All right, so that's the only thing I came prepared with. So hopefully you have some questions. All right, so we'll do both the amine and the enamine, and hopefully I can squeeze them onto one page so we can see the similarities between them. All right, so let's start with the amine, and say maybe we have this amine. Okay, we want to hydrolyze it. So as far as predicting the products, you want to be able to do that, but you also want to make sure you know the mechanism for this. Okay, so the hydrolysis, you can write it as H plus some water or H3O plus, something like that. Okay, now the carbon that's double bonded to the nitrogen after hydrolysis becomes an aldehyde or a ketone. Right, in this example, a ketone. And then the nitrogen, it comes off, and you just add 2 hydrogen to it to get the amine. Okay, if you're just doing a catalytic amount of acid, you can stop there. But if you do have a whole bunch of acid around, remember we just talked amines are bases. So if you do have a full equivalent of acid, then that amine will get protonated. Okay. If it's not specified, though, typically for hydrolysis, you can just assume an acid catalyst. All right. So the mechanism. All right. I'm going to use equilibrium arrows because that is what's truly used in the mechanism. It is equilibrium. But that's not a big deal. So if you have to do this mechanism, you can just use regular arrows to get from step to step. Right. So we have our acid. This imine is a lot like a C double bond O. Right. The first step with a C double bond O, protonate the oxygen. Right, the amine is going to be very similar. So protonate your nitrogen. Okay, now that's activated, meaning it's extra reactive. Now the water can add in. And that water adds to the double bonded carbon just like a carbonyl. I forgot my methyl group. Draw your methyl group in there. Don't forget it. Okay, so you get there. From here, so during the hydrolysis, your goal is to get rid of the nitrogen. Right? So the thing you want to get rid of, that's what you always want to transfer your proton to. Okay, so we want to keep the oxygen, get rid of the nitrogen, so do a proton transfer, and transfer the proton from the oxygen to the nitrogen. Okay, now I usually don't draw arrows for that step because we are kind of taking a shortcut here by not drawing the two proton transfer steps, but again, I'm totally fine with using that shortcut. Okay, now you added the proton to the nitrogen. It has a positive charge. It's now a good leaving group. So use a lone pair on the oxygen. Push that down, and then lose your nitrogen leaving group. So that's where your amine comes off, and now you have this protonated carbonyl. And your last step to get to just the carbonyl is use a base to take that proton off. So draw a long equilibrium arrow. Take that proton off, and you're done. Right? Yeah.
Can we use just B for the base, or do we draw, for example, water in the exam?
You can use B, or you can use anything with a lone pair. So you could use another molecule of amine as your base. You could use water with its lone pair as a base. You could even use this amine that fell off as the base. So anything that has a lone pair. But if you want to keep it generic and use B, that's totally fine. Yeah.
So the equilibrium arrows don't matter for the exam purposes?
No, you don't have to draw the equilibrium arrows.
Does that get for all the mechanisms for this exam?
Yes. So if you could just get through the mechanism with regular arrows, I'm totally fine with that. Okay. All right, so now let's do the enamine hydrolysis and kind of compare and contrast. All right, so it's the exact reverse of enamine formation. All right, so we're using acid and water, and the product's a little, just slightly more difficult to predict than the amine, but not substantially. So you have the alkene carbon bonded to the nitrogen. That becomes the double bond O in the product. So you lose that alkene, and the carbon bond to the nitrogen is double bond O. And then the nitrogen group comes off, and you just add one hydrogen to it. So that hydrolyzes, in this case, to a ketone and secondary amine. All right, so the major difference in terms of mechanism is just really the first step. You're still adding a proton, but if you look at the enamine formation, the last step is you lose the proton from like the carbon next to, or to form that double bond. So for the reverse of this step, you use this double bond. This is kind of like, remember adding acids to double bonds in organic 1. Okay, so use your double bond, protonate. We're going to add the hydrogen to this side on the right, and that will leave us, you can do a carbocation there. Let's go ahead and just do it like that. So you add the hydrogen there, and a carbocation. Then you can draw a resonance structure that moves that lone pair down. Now, in class, I think I did that all in a single step. So if you want to go directly to that structure, just in this first step, push that lone pair down at the same time as you move that double bond to the proton. And that'll take you directly to that structure. All right, so that's up to you how you want to do that one. All right, now from there, so that's the main difference in mechanisms. From there, pretty much everything's going to be the same as this positively charged nitrogen in the imine hydrolysis. So now we add the water in. Okay, so then you want to transfer the proton from the oxygen to the nitrogen. Okay, so you get the positively charged nitrogen that's a leaving group. Then use the lone pair on the oxygen, push that down to assist you in kicking out the amine leaving group. So there's your amine, protonated carbonyl. And then finally, just like we did here, in the last step, use a base. And take that proton off. All right, so if you're good with the first mechanism, the second just requires one subtle adjustment in the first step. All the other steps are the same. Two other things that can be hydrolyzed. So the first one is an ester. Right, so carboxylic acid derivatives get hydrolyzed to carboxylic acids. So when this gets hydrolyzed, the portion from the carbonyl, that becomes a carboxylic acid, so that's one product that you should draw. And then the O alkyl group, that comes off and just becomes an alcohol. So that's the second product you should draw. The other one, or one of the other ones, is this is an acetal. So upon hydrolysis, you're effectively breaking these two bonds, and that acetal carbon, just kind of like we did with the imine and enamine, that becomes a carbonyl, a ketone here. So that's that carbon. And then these OR groups, those come off as alcohols, so ethanols. Okay, since it's the same thing, you could get away with just drawing one, but if you want to be nitpicky, you could draw both of those alcohols that come off. Yeah.
So in class, the other day we did
Let's say we have this amide and we do the acidic hydrolysis. Okay, so you go through all of the mechanistic steps, but just as far as predicting the products goes, like before, or just like we did with the ester, this bond between the carbonyl and the nitrogen gets broken. It's a hydrolysis of a carboxylic acid derivative, so the carbonyl product is the carboxylic acid. And then the nitrogen portion, that comes off as an amine. Now, if you didn't use a full equivalent of acid, you could certainly get an acid-base reaction between this amine and the carboxylic acid. That's certainly possible. But this is one of the ones that I specified. We do use a full equivalent of acid because, actually just doing this first step here isn't energetically favorable because you're starting with an amide, which is more stable than the product of carboxylic acid. So this requires a driving force step, and that is the full equivalent of acid, so that as soon as a molecule of amine is formed, whatever your acid might be, if it's HCl or sulfuric, whatever, it'll immediately react with that. And it reacts with the acid even faster than the carboxylic acid because the acid you're using is stronger. So if it was HCl, you would get this ammonium salt. So, once this reaction's all said and done, one product would be your carboxylic acid, the other, the ammonium salt.
When you have a weak nucleophile, when do you need to activate the C double bond O? Is it always, or are there some cases where you don't?
So weak nucleophile, guess So there's a lot of gray area there, but
Because sometimes in the question paper I see without the hydrogen, and sometimes I see it with. So
right.
I'm
So basically, if you have a weak nucleophile, see if I can at least make this a little bit black and white for you. All right, so just our common weak nucleophiles, we use water, alcohols, and various amines. Okay, so we have reactions of these involving aldehydes and ketones and carboxylic acid derivatives. So if you have an aldehyde or ketone plus a weak nucleophile, eventually these weak nucleophiles will react with that. But every example we did, we added acid to catalyze the reaction. So let's just say to make it happen at a fast rate, you need acid to catalyze the reaction. Right, so then we have, you can react these with the carboxylic acid derivatives. So we did the acid chlorides, anhydrides, esters, and amides. The acid chlorides and the anhydrides, you don't necessarily need to activate these with acids, but what we did for most of these, we added pyridine to help speed the reaction up. And except in the case of the amines where the amine just acts as both the nucleophile and the base. So maybe to kind of answer your question, like the one case where you really just add a single thing to a carbonyl compound to get product is acid chlorides and anhydrides plus amines. That's really all you need to mix together. The esters and the amides, for these, if we were converting these to something else, again, they don't typically react by themselves, so you're adding the weak nucleophile plus an acid. So that would be an example like the ester, the Fischer esterification. Or, I'm sorry, I'm thinking carboxylic acids. But if you, mainly hydrolysis is really all we really did with these. So you're adding water. Water's the weak nucleophile for hydrolysis, but you add either acid to catalyze it, or you can add base to catalyze it. Does that answer your question mostly?
Yeah.
All right. All right, so I'm going to show you, these are probably the three most common cases of reactions where we would want an alcohol protecting group. So let's start with this first one and say we wanted to oxidize that aldehyde to a carboxylic acid. So using a harsh oxidizing agent, and what we want is this. All right, but the problem is that this harsh oxidizing agent will also oxidize the alcohol, so you don't get what you want. In reality, you would get this oxidized alcohol. Another case, let's say we take this ester and maybe you want to reduce it with like LAH. So you desire to reduce this ester to the alcohol. So that's what you want, but once again, this hydride agent is problematic with alcohols. So what happens is that hydride acts like a strong base and comes over and grabs that proton. So you basically just kind of quench your reagent and deprotonate the alcohol so you don't do what you want. Then one third case where you're using a harsh reagent that will affect an alcohol is something like Grignard or organolithium reagents. So let's say you want to add the Grignard reagent to this carbonyl. And get this after workup. Well, just like the hydride, this Grignard reagent does not interact well with alcohols. So it'll just come over and grab that proton. So I would say these are kind of your three most common reactions that we've covered where you really want to be on the lookout for problems with alcohols. So if you have one of these problems, then you want to use a protecting group. So let's just work from this bottom example. So our workaround is to protect the alcohol. Okay, we protect it with a silicon group. Okay, I'm just going to use TMSCl, so that's trimethyl silyl chloride, but it could be like any carbon groups on there. All right, so what that'll do is put this trimethyl silicon on the oxygen. So we get that TMS group bonded to the oxygen. Now you no longer have an alcohol to cause you any problems. So now you can do the Grignard reaction. So we'll just do that, followed by either an aqueous or acidic workup. Okay, but then you want to get your alcohol back out in the end, so you need to deprotect it. One of the reagents the only reagent we talked about for this is TBAF, tetrabutyl ammonium fluoride. Right? But really all that means is you have a fluoride source. And that fluoride will react with the silicon and pull it off of the oxygen. Then there's actually some water in here also. That'll just protonate the oxygen and you're at your desired product. But you would use the same workaround for all of these. So this one on top, you would add the TMS chloride to protect it, do your oxidation, then add fluoride to deprotect it. We'll start with that first example. All right, now, granite, this one, the easiest way, if I just wanted the ketone, I could use PCC. That doesn't affect an aldehyde. And I would be done. But let's say you didn't know the PCC reaction and you wanted to use a harsh condition. Well, if you want to use those conditions, those will oxidize the alcohol, but also the aldehyde. So you get that. So if you want to use those harsh conditions, or maybe you don't have PCC in your lab and you need to use just the chromic acid, but you want to stop just oxidizing the alcohol, you can protect the aldehyde instead. So the way we protect the aldehyde is through a cyclic acetal. So typically we just use this 2-carbon diol and some acid, and that will form a cyclic acetal at that aldehyde. Just like that. Right, now you don't have an aldehyde to worry about, so you can use the harsh oxidizing agent. And oxidize it. And then your deprotection just involves hydrolyzing that cyclic acetal. So hydrolysis is always acid and water. Right, so if you have an aldehyde or ketone that you think is going to be problematic in a synthesis, let's say, another example, if you have an aldehyde or ketone, you don't want it to react with a Grignard reagent, or maybe you don't want it to react with a reducing agent. You can always protect it as this cyclic acetal to keep it from reacting. So you protect it, do whatever reaction you want to do, and then deprotect it. All right, so in terms of functional groups that can get hydrolyzed, you can have, from the aldehydes and ketone stuff, you can have acetals, hemiacetals, imines, and enamines. So here we have an enamine. Here we have, I guess I should include the carbon. Here we have an acetal. Right? And then from the carboxylic acid derivative stuff, any of those can be hydrolyzed. So the nitrile is a carboxylic acid derivative. the ester is a carboxylic acid derivative. All right, so if you're doing this, sometimes it actually helps to not do too much at once and just do one group at a time. So let's go through and we'll just do, we'll start with the acetal. Right, if that gets hydrolyzed, this carbon becomes the carbonyl. So that becomes a C double bond O. And then these two OCH3 groups come off and become alcohols. All right, we don't need to write it twice since they're both the same. If you want to write that, okay, so we do that. Next, let's hydrolyze the enamine. All right, we already did one of these today. So that carbon that has the double bond and connected to the nitrogen, that becomes the carbonyl carbon. And then the nitrogen comes off and becomes an amine. Okay, so we have that. Then let's do the ester. Oops. So the ester, that'll get hydrolyzed to a carboxylic acid. This oxygen group will fall off to become an alcohol, CH3OH, and the carboxylic acid. Let's get those two pieces. All right, and then finally the nitrile. That will get hydrolyzed. The carbon of the nitrile becomes the carboxylic acid. Right? The nitrogen comes off, and you just add enough hydrogen to it to get to the amine. Just like all of these other things that fell off, you just add enough hydrogen to give it its requisite number of bonds. So there's the nitrile carbon, that becomes the carboxylic acid. The nitrogen, this becomes NH3. So our final products, we get this, NH3, methanol, dimethylamine, and more methanol. All right, so if you have something like that, you can do it step by step, or if you feel comfortable with it, you can do everything kind of at one time. All right, any other questions? Yeah.
What did you say was hydrolyzing again?
I can write them down for you. acetals, hemiacetals, imines, and enamines. The acetals and hemiacetals will hydrolyze to give you an aldehyde or ketone plus alcohol. Imines and enamines will hydrolyze to give you an aldehyde or a ketone. Plus an amine. Okay, and then your carboxylic acid derivatives. So carboxylic acids, those can't be further hydrolyzed. That's as far as they can go, but all of their derivatives can be. So acid chlorides, esters, amides, anhydrides, and nitriles, these will all hydrolyze to the carboxylic acid plus the leaving group with a hydrogen on it. So the acid chloride, the Cl comes off. You compare that with the hydrogen as HCl. An ester, the OR group comes off, so HOR will be the alcohol. The amide, the nitrogen group comes off, put the hydrogen on that to get an amine, and so forth. So those are all of your hydrolyzable groups. Right, so don't get that confused. So these hydrolyze to give aldehydes and ketones, but aldehydes and ketones themselves are not hydrolyzable. Those don't hydrolyze into anything. Right, anything else? Yeah.
Can you go over the anhydride mechanism?
With, do you know what you want it reacted with? An alcohol, an amine?
Whatever one we did in class, I guess.
You're expecting me to remember, huh? Let's just do, we'll do one with an alcohol, because I can't remember what we did. Right, so we'll do the anhydride plus methanol. And with these, we add pyridine to speed them up. Right, so for this, it's not acidic conditions, so you can't protonate the carbonyl first. All right, so the first step is just adding your nucleophilic oxygen to one of the carbonyls. Okay, so we add the methanol in, right? We get the tetrahedral intermediate that always breaks back down. So those electrons will come down, but instead of losing the methanol we keep. Here we lose this leaving group, which is an acetate. Methanol is still attached. Okay, and then finally, your pyridine, which is just a nitrogen base, that will take the proton off of the oxygen. there's your product. If you want to draw the protonated pyridine byproduct, you could do that too. But when I ask for major products, the pyridinium ion isn't one of those. All right. Yeah.
You can add an acid to this reaction to make it faster, right? And if you
So all right, well, we didn't do that, but yes, you could. So you could do this, you could get rid of the pyridine, so you wouldn't want to mix the acid and that weak base, but you could do acid and the alcohol and do an acidic mechanism to do that too.
and then if you do add the acid, it would protonate the
Carboxylate here.
yeah, that one. Would that also count as a primary product or a main product?
No, again, it's typically like the high molecular weight product.